All right, should I do it real quick?
Yeah.
Okay. There was a homework problem similar to this, except it was just cosine. Sorry, it was just square root of x. So I just changed a little bit. So let's do this real fast. So you have y was cosine hyperbolic inverse of, square root x squared plus 1. So this is some chain rule here, right? So what is the derivative of cosine hyperbolic inverse of x according to your formula sheet?
It's 1 over the root x squared minus 1.
X squared minus 1? That it?
Yeah.
Okay, so all we need to do here is do 1 over the square root of x squared, but for us, x is the entire quantity there, right? X squared plus 1 squared, and then minus 1, right? So that's a derivative.
Well, I thought it'd be square root.
Yeah,
It's square root.
Yes.
You're scared.
Yeah, sorry. Yes, yes. But, okay, you're going to square the square root, so, sorry. Yeah. There we go. And then minus 1. There we go. You could do that. Yeah. That's the beginning, right? Now you go inside. You take the derivative of the square root of this stuff. So 1 over 2 square roots of that stuff. And then keep going with the chain rule. 2x. 2's cancel. This square root and that square, so I don't know, looks something like 1 over square root of, what is this? X squared plus 1 minus 1, so just x squared. And then times 1 over the square root of x squared plus 1, and then you still have times x out there. Yeah. This actually turns into x, right? Now, technically speaking, it should be absolute value of x. Anytime you have the square root of x squared, this is really the absolute value of x. Think about that for a second. Make sure you understand that. If you say x squared square root equals x, that's true as long as x is positive. But what if x is negative? So like, let's just take a number here. What's 3 squared square root? Well, that's 9, right? Square root of 9 is 3, so that's correct. But what if that had been negative 3? Well, it's going to be 9 still, square root, and that's going to give you 3, right? So here you plug in x, you get out x. Here you plug in negative x, you got out x. So it should technically be the absolute value of x there. A lot of times we just kind of like skirt around that, but now we need to like pay attention to that a little more. So this is going to be absolute value of x. And so we have something like x over the absolute value of x times 1 over square root x squared plus 1, something like that. I would have taken it less simplified, that's okay. But I'm looking to see that make sure you could take the derivative. All right? All right, I'm not a big fan of quizzes, all right? That ate almost 15 minutes of class up for one problem to me. That's why I don't like quizzes. And to me, this is a pretty simple problem relative to, what we're doing in this section. So I just want to make sure this first day or the first week back, that y'all are keeping up with this a little bit. So, all right, today, so I'm going to give you some options. What we're going to start today is antiderivatives, and I'm going to give you a choice. The class is going to vote here. We're going to spend the next, well, it's going to go all the way till right around March. So we're going to spend until about March 1st on trying to find antiderivatives of functions. That's what we're going to do. Then at the end of that, we're going to talk about like how we can use those antiderivatives to do things, all right? Your choice today is, would you like to see a little bit of where the antiderivative is used, like its value, before we start spending a month on trying to find antiderivatives, or you just want to do it more mechanical, like let's just find antiderivatives? So vote to peek into what are called Riemann sums a little bit to get some sort of idea of why we need them. Okay, and then, all right, I think that's a majority. All right. Now, we are going to cover this section anyway. All right, it's just a matter of we do it now or we do it later. So we'll do this one right here. We won't spend all day on it, but I'm calling it Chapter R because it's not in the book. Well, pieces of it are in the book. It's called Riemann Sums. I just kind of pasted together a bunch of stuff from the textbook. And to get us started, I have a little handout here. I'm going to give you in your table about 5 minutes max to just look at the following picture. Let me get this handed out first.
Thank you.
You're all alone out here. You're welcome to join a group if you'd like. I might have an extra in there. I don't want you to go try and do this, all right? What's wrong? You thought you heard thunder? Or it was thunder? It's all right. Keep it. So 5 minutes tops here. Don't try and calculate anything. I want you to just talk about how you would go about trying to find the area of this gray region. Okay? How would you do it? You're supposed to pretend like you've never seen calculus. You know what I'm saying? Like, there's an obvious answer if you know what a definite integral is, and that's. I mean, they're.
When you say antiderivatives, you mean integrals, right?
Kind of.
They're not the same?
Not exactly. Yeah, I mean they are connected, yes, but we're going to have to be clear on that language. Okay. Just look at it like you're back in the 18th century and you're trying to figure out that. No Google?
My suggestion. Good.
Nah, it's just drizzle. Come on.
Yeah, look at this one here. That's nice. Nice view, right? I don't even know.
No? Y'all have any ideas?
Square total and trying to
You're a farmer. This is your property. You know, you're trying to figure out how much acreage you have. You know. How could you estimate it? What's that? Yeah. So we'll talk about it after a couple of minutes here. I'm going to ask each table for their opinion.
That's definitely not even hugging me.
Y'all want a little more time to think about it, or everyone have some idea of how they would do it?
whole thing and the other someone forget about me. That's real. I get that too.
Okay, let's go around the room. Let's talk about it. Let's see. Ian, James, Kyle, and where's your name thing? Do you have your little name thing? Any ideas? Were you here on the first day? No. Oh, you didn't? Okay, I'll get you a little piece too. Any ideas?
Kyle led off with the idea that if you go from the vertex and make the box in the shaded area below the graph, that accounts for the big. So you basically from the vertex you make just a straight from the vertex from the lowest point of your curve.
Okay.
You make just like
Oh, straight across.
straight horizontal line, and now you have one very lovely square to account for area and two almost great right triangles. You know, there's a little tiny area that would have to be either accounted for
I like
by
that.
either smaller triangles or deviation or something like that.
Okay, I like that. Joel, did you come up with anything? So just start with the whole thing being a rectangle and then try and maybe like take stuff out. Okay? Anything different? Anyone have any other strange approach? What did y'all have?
The same thing, a rectangle, and then you subtract two triangles from a
So you were going to take out triangles from in here?
Yeah.
Okay. Yeah. Any other variations that you want to mention? So this is a fundamental problem that we had as evolving species here, is how to figure out something like this. Right? There was no formula for it. Now what we did have was an agreement upon how to measure the area of a rectangle. So we all agreed that if we knew this side was 5 and this side was 3, we could define the area in there to be 15, right? So length times width, that gives you your area. That we all agreed upon. And then when it came to something like a triangle, that was easy for us to determine a formula for also, right? If someone gives you a triangle, and it does not have to be a right triangle, the area of this is what? 1/2 base times height, right? Where the base is the distance from here to here, and the height is that right there. Yeah? Okay. So that formula, where did we come up with this formula?
It's half of the square.
It's half of a rectangle,
Or a square.
something like that, right? So yeah, all we did was we said, all right, take this picture, right, and draw another one upside down. That's not a very good picture. It's closer to this. So that's that same triangle drawn, turned, and pasted. Do you see that? And then if you come in here and there's that height, right? If you take this piece and you cut it off and you slap it right here, right, like this, then you've created a rectangle. And the height is this. And what's the area of the whole thing? Base times height, but that was you doubled the triangle, didn't you? So you half that and you get your area. So that makes sense. Hopefully that makes sense to you. So we could do triangles and we could do rectangles pretty easily. And then we were faced with something like a circle, right? So that's the classic problem. You know, what's the area of a circle? So that's does that seem to you to be the next object that would be something you'd want to go after, right? I mean, once you got rectangles and triangles, circle seems like the next one. And so, you know, how do you do this? Well, unfortunately, you can't fit a rectangle in there. You can't fit a triangle in there perfectly. You're always going to have some error to it, aren't you? Okay. Just like on the estimation you just did. So that's what we did. Now, this little animation shows that a little bit. You know, what we could do is we could take the circle, we could break it up into some triangles like that, and we could estimate that, right? And so this like pinkish region is the approximate area. So everything in yellow is what we'd be off by, right? The error, E-R-R-O-R. And then we could try something else. We could say, okay, those rectangles were too big. Those triangles were too big. Let's take smaller triangles and add those up. And now we have error. Our error is getting a little smaller, right? And then if we do smaller triangles, then the error gets smaller and smaller and smaller, so on and so forth, right? But it's still there. Yeah? So this is known as the method of exhaustion. Was that up here already? There it is. This is called the method of exhaustion. And the Chinese did this and got a very good approximation for the area of a circle using the method of exhaustion. You know, just drawing a very accurate picture with very accurate triangles, and they got something pretty close to the formula. I mean, what's the formula of the area of a circle that we know? Pi r squared, right? And they weren't able to get pi exactly. Does anyone know what we used for a long time to approximate it? 22/7. That's what we used for a long time, 22/7. If you do that on your calculator, what do you get? You got your calculator there. 3 point something, right? 3 point what?
1415.
Is it? No?
I got 3.14286.
286. So you're saying 3.1415 is pi, the first few digits of pi. So the first first two decimal places of this and that match. So they were off by tenths, hundredths. They were off by like 1/1000th. That's pretty good. That's pretty good, you know, considering all you had was pieces of paper and straight edges, you know. So method of exhaustion. So how is this connected to what we're doing? And well, I'm not going to go through the whole Riemann sum thing. I'm just going to show you the development of it. So if you take something like a picture where you have time, you can look at it up there, and then you have your speed here, and you have a measurement here of 2, and over here 3. The question is, this is in miles per hour. The question is, how far would you have gone? What's the total distance you would travel? If I told you you were traveling a speed of 2 miles per hour, and you were traveling that speed for 3 hours, right? Then what would your total distance have gone? Well, I mean, what's the total distance you will have traveled? 6 miles, right? 6 miles? Everyone agree with that? But that is just geometrically the area below that line, isn't it?
Right.
So the area of that curve looks like possibly it is connected to the answer to that question. That the 6 here is equivalent to the 6 that you would get for the total distance traveled. Make sense? So what if the picture becomes a little more complicated? What if instead your speed looks like this? So take a look at that for a second, read it. So if that's your picture, okay, and it might be better if I get up there and do it. Where's my straight edge? Might be easier for us to draw some lines here. We want to know how far the person goes between hours 2 and 5. So that would be like here. I missed it. There. And then 5, let's say 5 is here. So how far would that person have gone? See, it's not as easy when it's just a flat, straight line, right? But if we believe the same connection that we had on the previous problem, then all we need to do is find the area under that, right? And so that we could do. This would be easy. We could break it up into a rectangle. This is exactly what your table suggested. We could find the area of this pretty easily, right? What is that area? How wide is this? It's 2 and 5, so that's 3. And then how tall is it? 1. So this would be 3. And then we find the area of this triangle, which would be, how wide is it? It's 3. And then how tall is it? 2. It's 2 units high. So half of base times height, so 3 again. So how far would this person have traveled? 6 miles, right? But again, it comes down to, can you find the area underneath that curve? Understand? Okay, so what do you think is coming next? Started with a flat line, very easy. Yeah, now it's going to get a little more complicated, right? So what if you have a function that is harder for you to tell? See, if we do something like this, I used x squared here. You can't do rectangles and triangles and get a clean answer, right? The perfect answer. You're going to always have a little bit of error. But if you try some method of exhaustion, you could get closer and closer the better your drawings are, right? The more little triangles you get in there. So Riemann, a mathematician, came up with a way of doing it. And he said, what I'm going to do is I'm going to approximate it with rectangles. So instead of using triangles, he just used rectangles the whole way. And these are called Riemann sums. It's the sum of all these little Riemann rectangles. And again, without getting into too much detail, we're not going to do Riemann sums by hand in here. They're torturous. There's a curve, right? If I want to know the area under it, I could do maybe, 2 rectangles. That would give me some approximation, right? That would be too much, wouldn't it? The gray area is way more than the area below the blue curve. But if I keep going 3, that's better. Can you all see these 2 numbers here? I know it's kind of hard to see for me. It says 58 up here, 58.5. That's the estimate. That's if you add these 3 rectangles together, that's the area. The actual area, the true area, is 41.3333 repeated. So we're off quite a bit there, aren't we? But if I do more rectangles, look at what happens to this number. 54 is going to start getting closer and closer and closer, right? And closer. But what happens is that at some point you have to stop adding, right? I mean, you have to say, okay, I'm going to add 100 rectangles, or I'm going to do 1,000 rectangles, or I'm going to do 1,000,000 rectangles, right? And that's the way college algebra was. But in calculus, we learned about infinite processes. We learned about this thing called the limit. The limit was a way of letting things go to infinity, right? You could let things go to infinity. So what Riemann decided is, what I'm going to do is I'm going to come up with a formula for that area based on n rectangles. And then I'm going to let n go to infinity. And when you do that, so let me flip to the next one here. You have to know some stuff about sigma notation, which again, I'm not going to test y'all on this. I'm just showing you kind of the development of this. What Riemann was able to come up with is this right here. And I want to show you, if I can. Ooh, that's too big. Well, maybe not. That's too big. There it is. This piece right here. Okay, so I want to explain to you, if I can possibly explain, what that piece is. So I'm going to write it up here on the board and try and help you visualize what's happening. So I have the limit as n goes to infinity, right? This symbol, which is what? Sigma. And then f of a plus k times b minus a over n, and then times b minus a over n. What the hell? So Riemann, this is a formula you can use to find the area under a curve. But you got to know what a lot of this shit is in here. There's a lot of stuff that you're like, what? What's a, what's b, what's k, all this stuff, right? So here's how it works. You have a curve, all right? You have some function here, f, that someone gives you, all right? It might be the function x squared, it might be something else. But you have to know how to draw this curve, all right? So that's given to you. You're given an endpoint A and an endpoint B, right? And we want the area in here. Let's talk about cutting this into rectangles, all right? So I'm going to cut this into these rectangles, and I don't know how many I'm going to have. Let's say there's n rectangles. So imagine there's n rectangles in there, right? Let's just look at one of those rectangles right now, all right? Just one of them. And I'm going to kind of put it over here on the side so we can kind of really focus our attention on it. And I'm even going to put the x-axis here like this. All right. How wide is that rectangle? So remember, we're going to cut this into n rectangles, right? And we're going to assume that each rectangle has the same width. Understand? So what would it be? Say again? Ny. Okay, that's a good guess. But it's not quite n. Think about it this way. If let's say that I had, let's say I'm going from 0 to 10, okay? And I cut this, and I've got my function here, and I put 10 rectangles in there. How wide is it going to be? 1, right? Okay, so let me give you something a little harder. How about if I go from 4 to 10, and I put 12 rectangles in there? How wide are how wide's each rectangle? So how much distance is between here and here? 6. And if I put 12 rectangles in there, then I take that 6 and divide it by 12. Each one has to be 1/2 wide, right? Yes? Okay, so let's go back over here and talk about how wide this rectangle is. How much distance do I have between here and here? B minus A, right? And then divide that by n, and that's how wide each rectangle is. Yes? Understand? Do you see that right there? Okay, now I'll tell you why it's there in a second, but I'm just asking you how wide this is. No one has a question on why that's B minus A over n? No? Okay. The next thing is, if each one of those is B minus A over n, then I want to kind of draw this a little bit bigger. So I'm going to draw that number line again. Imagine that the function's up here. Here's A. Here's B. This would be the first edge of the first rectangle, right? So the rectangle goes up and over and down. Yes? Okay. Do you agree that this would be A plus something? Like to move to the right, I have to add something to it, right? How much do I have to add to move to the right? The width of the rectangle, right? How much is the width of the rectangle? B minus A over n. Yes? And that would be that point? Yes? How about the next edge of the next rectangle? What would that be? It would be that plus another one of those, right? Another B minus A over n. So could I write it this way? A plus 2 of the B minus A over n's, right? That would be start at A, move 1, that's this one. Start at A, move 2 of those pieces, widths of the rectangles, you're here. And then what about this next one? Same thing, A plus 3 of the B minus A over n's. Do you see this right here? That's where this is coming from. See, K is the number in front. And K is going to start at 1, then go to 2, then 3, then 4. I'm going to try and put it all together here in a second. I'm just trying to get you to identify pieces of the picture. We okay? Okay, so we have a width of the rectangle. We know that never changes, right? We know that each right endpoint is one of these, right? One of those? Okay, so let's go back to this one. Tell me what right endpoint that would be. Well, we don't know, right? I mean, like we just picked an arbitrary rectangle in here? So wouldn't that right endpoint be A plus, I don't know how many? 1, or maybe it's 2 or 3, right? Why don't we just say K of them? I don't know what it is. B minus A over n. Okay, so do you agree with me on this? Okay. We know the width of this rectangle. To find its area, all we need is what now? We know the width is b minus a over n. All we need is what? The height. How tall is that rectangle? Well, remember, that's supposed to come in, right? And the function's here somewhere. And I want to approximate how high that is by picking a point off the function. Wouldn't this red point be equal to what I get when I plug this point into the function? Evaluate the function at this point. Well, what's the point that I need to plug in? This one, right? That's this. You see that? That's the function with the right endpoint of the rectangle plugged in. That's the height times the width. The width never changes, does it? The only thing that changes is that you first want to get the first rectangle. Let me put this all together. I think some of you are getting it, and that's all I hope, is that maybe like half of you are with me. If you're not, that's okay, because at the end you're just going to get a formula. But I want you to see that this is not just some random crap thrown up on the board. Okay, it comes from something. All right, so I'm going to look at the formula for each rectangle now. I have these rectangles, right? We have n of them. I don't know what they're doing, right? There it is. This first rectangle, rectangle 1, what would its area be? Well, it would be f of a plus one of those b minus a over n's times b minus a over n. So let's see if you agree with me on this. Here's a, right? I'm going to take this point, go up to here. That point right there was a plus b minus a over n, wasn't it? One of those jumps. So that's that right end point plugged in to the function, and then this is the width. Yeah? That's rectangle 1. What's rectangle 2? This one. So now I'm at this end point, right? So I'm going to take the function a plus 2 of those, b minus a over n's, times b minus a over n. Right? What's your question? You can see it on your face. You have to add another one. To get to the next endpoint, the next one's going to be what? 3 of these? And then 4 of these? This never changes. That's the width. The width is always the same the whole time. Yes? So it's height times width, or width times height, width times height, width times height. The only thing that's changing is the height is changing, and it is dictated by the function, isn't it? Okay, so I need to take that answer, add it to this answer, right? Take that answer, add it to this answer, that answer to this one, and go all the way and add all n of them up, right? What's a short way of saying that? We use this notation right here. This is sigma notation. This says add up this expression starting with k being 1. So first let k be 1. If k is 1, what is this? Rectangle 1, isn't it? So take that answer, add to it, now let k become 2. This is this with that being a 2. That's the only thing that changes. And then that's the second rectangle, yes? And then you go and you let k become 3. And that'll give you the third rectangle, won't it? And you do that to n, all the way to n. You stop, and that's your answer. Yeah? But you then let n go to infinity. And what happens is, and this is where the limit comes into play, what happens if n goes to infinity? What does this go to? 0. Right? 0 times what happens here? That goes to 0, which means just f of a, which is just the left endpoint. But we saw in Cal 1, just because something goes to infinity or 0 and something else goes somewhere else, right? That your answer is not necessarily 0, right? This can actually go to a place other than 0. We ran into this in Cal 1. Indeterminate forms. So Riemann has found a way for us to actually find the areas using this formula. Does that seem pretty? Yeah? I mean, it's not like super crazy math here. I mean, it's very geometric. Can you see the connection there? Now, the beauty of what we're about to do is that, and this is where what's called the fundamental theorem of calculus comes into play, is we're going to learn later, okay, that if you want to look at something like the function, let's say f of x is 2x, all right? And let's go between 0 and let's say 5. Can somebody tell me what this area is? Just by using a triangle, what's that area?
You get 10.
10? How are you getting that?
You go up to. Right?
So 5 times 2 would be, this is 10, right?
Okay.
So what's the area of that rectangle? Well, how wide, I mean that triangle, how wide is it? 5 times 10 is the height, but then half of it, right? So the area of that is what? 25? Okay. Yes? All right. Now, Riemann would be able to handle this if it was curvy. Yes? That's what I've tried to convince you of. He could handle it if it was curvy. We are studying antiderivatives. Why are we studying antiderivatives? Because of this. Can somebody tell me what the antiderivative of that is, even though we haven't talked about antiderivatives? Tell me what function I would take the derivative of to get that. X squared, right? Does everyone agree that if I take the derivative of this capital F, I get little f? So we call this the antiderivative. Okay, hold on, you're ahead of me. We call this an antiderivative of this, yeah? Now watch. This is the amazing part of the fundamental theorem of calculus. What were the two endpoints here? 5 and 0, right? I'd like you to take 5 and plug that in here. What do you get? So if I plug 5 in here, I get 25. Now what I want you to do is subtract from that what you get when you plug in 0. So plug 0 into this, and what do you get? 0. What's the answer? 25. Coincidence? No. That's the way it will always be. And so in other words, Riemann found a way of, it's a method of exhaustion, basically. He was able to find a way to find the area under curves, but it required these sums. And these sums get really, really nasty. Then the fundamental theorem of calculus came along, and we were able to determine, hey, guess what? This area under here is actually connected to the antiderivative of the function. If you can find that antiderivative, you can find that area with very little work. All you have to do is just plug 2 numbers into this and you're done. The trouble is going from here to here. In this case, it's easy, and now we're going to spend a month on figuring out how to go from here to here. Understand? Okay, so I'm just trying, this was just about trying to motivate the idea. We will be able to find areas under curves if we can find antiderivatives. And then once we do that, we can just do a bunch of stuff. I mean, because what happens later is that we can use the same principle that Riemann did, all right? If I take this function, right, I think most of you understood that to find the area, I cut it into a rectangle, and I find a formula for that rectangle, and I add them up, right? I add them up forever. I add an infinite number of them up. So we talked in the beginning of class, I told you that we would rotate this around the x-axis at some point. Did I tell you all that? Okay. So imagine I rotate that around the x-axis, and I get this solid, right, that looks something like this. Right, it's solid. And we want to know the volume of this. Well, we can actually come up with a way of doing it with almost like a Riemann sum. So let's take, again, a rectangle out of here. And what we would do is imagine just wrapping the rectangle around the x-axis. What would that rectangle wrapped around the x-axis look like? Like this? Like a coin, like a quarter or a nickel turned on its side? Something like that? Do you know a formula for the volume of something like this? It's a cylinder, isn't it? It's a cylinder. So you could come up with the volume of this thing, couldn't you? Right. And if you have the volume of one little piece, then you should be able to come up with the total volume if you just add all those pieces together. Just like we did with the area, right? We found the area of one rectangle and then we added them all up. Well, if we can find the volume of one of these and add them all up, then we should be able to get the volume of the whole thing. Same fundamental principle as the Riemann sums. How about if we take this and we have another curve on the bottom and we rotate that around the x-axis? What's the difference? It'd be hollowed out, right? You would have this, and on the inside, you would have that. So now you have a washer, don't you? You put your hand through the center of this. Now we can still find a formula for the volume of this. It would be the volume of the solid cylinder, take out the middle part, the smaller cylinder, right? But again, if we can come up with a formula, then we should be able to add them up forever. And that's going to be key later for you to be able to see the geometry behind this. So that's why I wanted to show you the Riemann sums, so you have some idea of where this notation comes from. All right, that's it for Riemann. We're going to get on to antiderivatives now. There's a lot of definitions in here. All right, so I'm not writing all this down on the board. It's all up there. It's in your notes so you can print online. A function capital F is called an antiderivative of little f on the interval I if the derivative of capital F is equal to little f for all x in the interval. Whoa, okay. That just means that you take the derivative of something, you get some other function. If that happens, you call that function you took the derivative of, you call it the antiderivative. Now, we have something called the general antiderivative, which is capital F of x plus c. So let's just see this in action here. Earlier, I had put this up here. F of x was 2x. And I asked you to find some function that when you take the derivative of it, you get that. And I heard appropriately x squared. And then I heard x squared plus c. And that's because you had seen this, right? But we could do x squared. We could also do x squared plus 1, right? Because the derivative of this would still be this. And then we could do any number we want right here, right? So that's why we say the general antiderivative will be this plus c. So how many antiderivatives are there for this? An infinite number of them, right? There's an infinite number. It's x squared plus any number. And when you add a number to a function, it just moves it up and down, right? Up or down, depending if this is positive or negative. So what happens geometrically is if you look at this line, 2x, the red one, if I graph the antiderivative, it's going to be this parabola, which is the blue one. And I can change the value of c, which would move it up or down. And if I show you a bunch of them, here's a couple of them, right? Here's more of them. Here's more. And more. I think I'll go back to this one. What we have is this. If I move, I thought I was going to be able to move. There we go. What do all those parabolas have in common? Look at those parabolas. Those are little tangent lines, right? Yeah. What's the same with all those? Same slope, right? Isn't the slope of a tangent line the derivative? So all those curves have something in common. All their derivatives are the same. Oh, that's exactly what we're saying, right? So that's why they all belong to that family. All right. I think we can all see that if you let f of x be 3x squared plus 10x plus 6, then this would be the antiderivative. And you just check it, take the derivative of this, and you should get this, right? Are we all comfortable with power rule? I hope. So derivative of this is this. And we can, again, look at the pictures and look at the family of functions, and we can see that they all have the same characteristic here, right? There's a whole set of antiderivatives that you need to know, and it all comes from Cal 1. The more comfortable you are with derivatives in Cal 1, the easier it'll be to find the antiderivatives. So I'll go up there and I'll point these out. Let's make sure we're all okay with these. Let's do the ones that are obvious first. Remember in Cal 1, the derivative of the absolute value of x is 1 over x. Derivative of the natural log of x is 1 over x, yeah? So that means the antiderivative of 1 over x should be natural log. E to the x was easy. Derivative of that is this. So the antiderivative of e to the x is itself. The derivative of sine was cosine. So the antiderivative of cosine is sine. This one's the tricky one. What's the antiderivative of sine? Negative cosine. People always say, they always mess this one up. They always say the antiderivative of cosine is negative sine. That's incorrect. Some of the other trig ones you should know. Remember that the derivative of tangent was secant squared? So the opposite, antiderivative of secant squared is tangent x. So these are the functions, these are their antiderivatives, yes? Everyone here needs to know these, all right? Just these need to be in here. Now the one I've skipped is this one right here. And that's what we're going to establish now quickly, which is called the power rule for antiderivatives. How many of you have seen the power rule for antiderivatives? I know everyone that was in my class did, yes? Okay, so here's the idea. If you have a function that is a power of x, and I'll put an example underneath this as an example, like x to the sixth, then when you try and find its antiderivative, capital F, what do you know about the power? What has to happen to the power? It's got to go up, right? Because when you take the derivative of a function, the power comes down, doesn't it? So when you take the antiderivative, when you go backwards, that power should come up. So whatever the answer is over here, it should be whatever this number is plus 1. 7, right? I just say 7? Yes? Over here, in more of a general formula, I would say that. But that's not quite going to work, right? Because if I take this right here, or let's say this one, if I take the derivative of this now, am I going to get this back? No, because that 7 is going to come down, isn't it? And I don't want the 7 there. So what I'm going to have to do is scale it out, right? I'm going to have to multiply by 1 over 7 in order to get the 7 to cancel. Out here, I would say 6 plus 1, which is 7. But I'm trying to get you to see the general formula. See, out here, you're going to scale it. You're going to multiply it by 1 over n plus 1. That's the formula that's up there, but they write it a little different. They write this. This and this are the same thing, aren't they? Okay. They just took this n plus 1, slid it underneath that. So I prefer this. You shouldn't. You can use this, but I don't think you should. Stick with that one. And then you have to throw a constant on the end of this to have the general antiderivative. And that should work all the time. No, there is a point where it doesn't work, and you can see it in the formula. It's if n is negative 1. Because if n is negative 1, you get division by 0. So we will say here at the end here that this formula works so long as n is not negative 1. But what if n is negative 1? So let's take a look at it. If n is negative 1, that's just 1 over x, right? And we already know the antiderivative of that. You told me earlier, right? Then that would be natural log of the absolute value of x plus c. This is what's known as the power rule for antiderivatives. It allows you to take the antiderivative of any power of x. You use this formula as long as the n is not negative 1. If the n is negative 1, then the antiderivative is just the natural log. So let's just do an example here, a couple of examples. I'm kind of moving fast here because I get a sense that a lot of you have seen this. How many of you have not seen it? Let's do that. Anyone not seen it? It's okay if you haven't. Anyone not seen? You have not seen this? Not seen this? Okay. All right. So I don't have your names. What's your name? All right. There you are. I kept it. All right, Jaime. All right, Jaime. So Jaime, you're going to have to tell me if you're not catching in this. And what was your name?
Gonzalo.
Okay. Gonzalo? Okay. You guys are going to have to let me know. Everyone lets me know if they're hung up, but specifically someone, people who have not seen this. If I'm just like going too fast, just slow me down. All right? So for part A, I'm given a function here, 2/3 x cubed plus 4 square root of x minus x square root of x. And we're asked to find the antiderivative. So there's some subtle things that we have to discuss here that I'm not putting up formally in the notes. Back in Calculus 1, if I had two functions that were being added together, and I asked you to take the derivative, right? We use that for the derivative. Could you just split this into two and take the derivative of each one? Yes? Yeah? The antiderivative works exactly the same way. If you have multiple functions separated by addition or subtraction, you can take the antiderivative of each one separately and then combine the answers together. So it works the same as it did with derivatives. That's good news. Also, in Cal 1, if you had a constant, right, times a function, and you took the derivative, what happens with the constant? That's if it's by itself. Right? The derivative of a constant by itself is 0. It would, the constant alpha, let me give you an example. How about this? 4 times x squared. What's the derivative? 8x. What happened with the 4? So the power rule happened on the x squared, right? 2 came down, x, 2x, but then the 4 just came along for the ride, multiplies times the 2 and becomes your 8x, yes? So the 4 came along for the ride. So the c comes along for the ride, and you just take the derivative of the function. C just multiplies it at the end. The antiderivative is going to work exactly the same way. If we have a constant sitting in front of a function, like here the 2/3, here the 4, here -1, it's just going to come along for the ride when we take the antiderivative. All right? So really when we look at this, we're focusing on 3 separate terms. All right? And within each of the 3 terms, we are ignoring, in this case, the 2/3, the 4, and the -1. They will just come along for the ride. Yes? And that means all of our attention is on x cubed, which is a power of x. Yes? The square root of x, which is again a power of x. And then x times root x, which is again a power of x. So let's rewrite the entire problem first before I try and find any antiderivatives. Let's rewrite it and make sure everything is written as a power of x. What's square root of x written as a power of x? X to the half minus, I'll put a 1 here even though I don't need it. What can I do with x root x? What's that? X to the 3 halves. You're doing x to the first power times x to the half power. Same base, add the exponents. 1 plus a half is 3 halves. Yeah? Okay. So x to the 3 halves? Pardon? Ah, great question, Alex. You mean like a backwards product rule? Because we're doing antiderivative. Okay. No. Because now that, so Alex is bringing up a great question here. We had x and root x, right? And we're trying to find the antiderivative. Yeah? So this is multiplication. The question is, can you look at the x by itself and the root by itself, find the antiderivatives and put them together? What do you think? Did it work that way when you were taking derivatives? Like if I asked you to take two functions that were being multiplied and take their derivatives, yeah, was that as simple as this? Is that what happened in Cal 1? Absolutely not. That's what made Cal 1 kind of tough when you got to derivatives, right? Once you got to these rules, the product rule is not this. The product rule is what? F prime g plus g prime f? And then it got even worse if it was a quotient, right? That was even worse. So when we go backwards, antiderivatives, it's the same disaster that we have here, but it's even worse because we have to actually try and figure out a way of undoing it. And that's why we're going to spend a month on it, because it's that difficult. All right? But if it's a sum, we're good. If it's subtraction, we're good. If it's powers of x, we're good. This right here is a product, but we can put these together into a single power of x, and that saves us. Understand? Okay. So are you ready to find antiderivative? Yes? Capital F of x equals, all right, so this 2/3 is going to come for the ride. Here it comes, just 2/3. Times, now I'm going to do my power rule on this. And since I've got Jaime, all right, what's the power, what's the n for us in the problem here? 3. So the formula is 1 over n plus 1 x to the n plus 1, right? That's what we need to do. So what will this piece be for us?
1 over 3 plus 1.
Okay, 1 over 3 plus 1. You want to just go 1 over 4? Yeah, that okay? And then x to the same number, right? 4? That's it. That's the first one. Any questions on that? Okay, we're going to move on to the next one. Plus 4. And now things get a little bit more challenging, don't they? Just a little bit? Because now your power is a fraction. So you still have to do this though, right? So it's going to look like this. 1 over n plus 1 x to the n plus 1. That's what we have to figure out. Follow this?
Yeah.
Okay. So you have to kind of get good at adding fractions and subtracting fractions in this class if you want to work fast. So 1 over 1/2 plus 1 is 3/2, but then flip it because it's 1 over that. So this is actually going to turn into 2/3, and that's just going to be slapped right next to the 4 with multiplication, and then x to the 3/2. We good? Everyone good? Okay. We're not done though, right? We have this last one, -1's coming for the ride. Okay. N for us here is 3/2. 1 over 3/2 plus 1 x to the 3/2 plus 1. So what is 3/2 plus 1? 5/2. Right? So 1 over 5/2 is 2/5. X to the 5/2. We're done with all the antiderivative stuff, right? Now, we always throw a plus c on here so that we get the general antiderivative. That accounts for the entire family of functions. And then we want to clean it up. That's not very clean yet, right? Question, Jaime? You're good? Okay, so let's just clean this up. What is this? 1/6. X to the 4th. Here, 8/3. X to the 3/2 minus 2/5 x to the 5/2 plus c. That's it right there. That's the antiderivative. And for those of you who have seen this before, can you share with me what the good news is about finding the antiderivatives? You can check your work. You'll know if you're right or wrong. How do you know if you're right or wrong? Take the derivative, and you better get back the original problem, right? Now, I think some people can attest that I can start checking these, but at some point, the checking is going to take forever.